In this section, we will be looking at exponential functions. Exponential functions are an important class of functions. We see this used in a lot of different practical real-world problems. Specifically for this class, the continuous compounded interest, any kind of compounding interest will be where we see these exponential functions being used. If you were looking at like other science classes, then certainly there's a lot of other opportunities for exponential functions to be used. Okay, so just to give us an overview of what an exponential function is, we've looked at quadratics before, which is where we had a 2 as our exponent and the variable was in the base. When we have one like this, the base is a number and the variable is in the exponent. And that's when it's called an exponential function. So if the variable is in the exponent, it's an exponential function. And that's the difference in these. So when you see an exponential function written, it will always be written as some base raised to the variable. The domain of an exponential function is the set of all real numbers, so we don't have to worry about limitations and restrictions. And the range is the set of all positive real numbers. This is just kind of looking at how this applies. So let's start, if we put -4 into this function, we would have 2 to the -4. And if you remember about your negative exponents, that's the same thing as 1 over 2 to the +4, which is 1 over 16. So that's where this point is coming from. If we did the same thing, 2 to the -3, that would be 1 over 2 to the 3rd, or 1/8. If we look at some of these others down here, 2 to the 0 power, anything to the 0 power is 1. 2 to the first, of course, is just 2. 2 to the second is 4, and so forth. So when you have a negative exponent, basically it's just going to bump it to the denominator. But that kind of gives you an idea of like how this function is growing. So it goes from 1 to 2 to 4 to 8 to 16. So because we have a base of 2, it's actually doubling for each increment of x. So if we plotted these points, you can see we have a graph. If we connected these, we would have a graph of a function that is increasing and increasing rather rapidly. And that's why exponential functions are often used to model virus and bacteria growth, because that's kind of how they grow. They just start out fairly slow and then they take off really rapidly. Okay. All right, so this is what a graph of an exponential function looks like. So if there's no number out in front of this, then it's always going to pass through this point 1 as a y-intercept. It also is always going to have a horizontal asymptote here at y equals 0. So that's its characteristic. Now, if it's shifted, left or right or up or down, it can change where that horizontal asymptote is. Okay, if we look at 2 to the -x, this one, if you look at these values, the values are actually decreasing. So if we connected this, we're going to have a graph that falls from left to right. So it is a decreasing function. Okay, and so this is a completed graph of it. Same thing as before, passes through the point 0, 1, and has a horizontal asymptote at 1, as long as that is not shifted and so forth. Okay, so a few basic properties here. The graphs always go through the point 0, 1, which we talked about, and that's because b to the 0 power is 1 for any base of b. Okay, so it doesn't matter which base you're talking about. The graphs are continuous curves, so they don't have any gaps or holes or jumps or sharp turns or anything like that. They're just smooth, continuous curves. We do have a horizontal asymptote here at the x-axis, like we've mentioned. If the b is greater than 1, then it increases as x increases, and if it's between 0 and 1, then it decreases as x increases. Okay, so looking at this one, is the graph of this equation a growth or a decay? And by growth, we're meaning does it increase? And by decay, we mean does it decrease? So looking at this, if I were to think of this in a little different form, the 1/2 is actually just a vertical shrink for us here. This is the exponential function itself. So going back to what we talked about before, when we have a negative exponent, that's the same thing as writing it as 1 over that. Okay. So it would be basically 1 over 4 to the x. And because we have it like that, actually I'm going to write it a little different way here. Okay, I want you to think of this as 4 to the negative 1 raised to the x power, okay? Because negative x is equal to negative 1 times x. So if I write it like this, then what I can do is 4 to the negative 1 power would be 1 over 4, and that would be to the x. And I've still got the 1/2 out in front here that is not affecting that. So when I look at this part here is actually the base. So my base of 1/4 is definitely less than 1 and it's greater than 0. So that tells me then that this is actually a decay function, so it's decreasing. If I had had something like 1/2 times 4 to the positive x, then the 4 would be my base and it would be greater than 1, so this would be a growth function. But anytime I have something like, let's say 3 times 2 to the negative x, if I have that negative x there, then we can always think of it as 2 to the negative 1 to the x, or 3 times 1/2 to the x. So these with the negative exponents are always going to be your decay functions. But I do want to review a few of the properties of exponent laws that we have here. So if you have like bases that you're multiplying together, then you would just simply add the exponents. So if I had an x squared times an x to the 4th, then that would be equal to x to the 6th. If I have a base that's raised to a power, I'm going to multiply the exponents. So that would be like if I had x squared to the 3rd power, I'm going to, in a case like that, I multiply those together. And so that would be x to the 6th power. If we have an equation and two things are equal to each other and the bases are equal to each other, then that's only true if the x and y are equal to each other as well. So that's just an important property to notice. Now that's not true if we have different bases. And same thing here, if the exponents are equal to each other, then that means, and the total expressions are equal to each other, then that means the bases would have had to been equal to each other. Okay, we've got a few practice problems here simplifying exponential properties. If you feel like you're good with this, and you can go ahead and give it a try, and if not, just watch as we go through it. So this first one is using the property where it's raised to a power. So these have understood 1 for their exponents, but that's going to be, I'm going to distribute that and multiply, so x to the 3rd and y to the 3rd. When I have one like this, I've got a couple things going on. I've got something raised to a power and I've got 2 parentheses multiplied. So if you remember back in elementary school, you would do, please excuse my dear Aunt Sally. And so that told us the order we needed to approach things. We deal with parentheses, then exponents, multiplication and division, and then addition and subtraction. So looking at this, what that tells me is I need to take care of this parenthesis that has this exponent first. Okay, so in doing that, I'm raising everything in here to this power. That means I'm going to multiply my exponent. So it would be x to the 2 times 4 would be to the 8th. and then 1 times 4 would be to the 4th. And then that's still multiplied by this over here. Okay, so now I'm going to take care of multiplying like bases. It's never completely simplified if I have like x's in two different places. They've got to be put together. So if I'm going to multiply these two together, then that means I'm going to have to add my exponents. So that would be 8 plus 1 would be 9. And then that would be y to the 4 plus 3 would be 7. And that would be my answer. On this one, I'm dividing, and one of our properties for the division is you want to subtract your exponent. So just like here, when you multiplied, you added the exponents. Here, you're going to subtract the exponents. So it would be x to the 5 minus 3, so x to the second power. If you have one like this, it's another case where you want to distribute it, and you distribute it to all the bases. So that's going to be a to the 4th over b to the 4th. All right, and then the last one here, one thing that I like to do is to try to get rid of negative exponents before I get started. And one way I can get rid of them is to simply move them. So if they're a negative exponent and I move it either from the bottom to the top or the top to the bottom, it'll make it become a positive exponent. So this x has a negative exponent. So if I move it to the denominator, it's going to get a positive exponent. The y to the third, I like it where it's at because it's a positive exponent, so I'm going to leave that there. This y has a negative exponent, so I'm going to move that to the top, from the bottom to the top, and it's going to go from a negative exponent to a positive exponent. And then I have this x to the third that's left here. Okay, so now these are multiplied together, so I can add the exponents. So that would be y to the 7th and x to the 5th. Okay, we have two bases that we see occur quite often with exponential functions. One is exponential functions that have a base of 10, because our whole number system is based on a base of 10. It's like the way we move our decimals and all of that is based on factors of 10. E to the x is another very special base for exponential functions. Both of these have their own key on the calculator, so make sure that you locate those and know how to use those. As far as how E is defined, E is actually defined to be the limit as x goes to infinity of this expression here. So in other words, as x gets really, really large, this is getting closer and closer to the number that we've defined to be E. Okay, E is an irrational number. So just like pi is 3.147, and it just goes on from there. It never repeats. We can't like truncate it at any point without it being just an estimate and not an actual correct answer for that. So E is the same way. E is 2.71, and it goes on forever there. So instead of like remembering another number like this, we give it the symbol E, just like we give this number the symbol pi. Both are numbers that occur very often in math. And you can see like from this table what's happening as we put larger and larger values of x in to this expression. This gets closer and closer to the actual value of what we use as the value for E. Okay, so we've talked a little bit about growth and decay with just a general base of B. The E, we said, is approximately 2.71. Okay, so because this E is greater than 1, that means that this one is going to be a base that's greater than 1, and it's going to be growth. Here we can think of this as e to the negative 1 to the x. So just like we did with the other bases, so that would be 1 over e Well, 1 divided by this 2.7 whatever is going to be less than 1. 1 over e would be less than 1, and therefore this is decay function. And you can see that with the graphs here. You've got growth for the blue one, decay for the red one. Okay, so using some of these properties to solve exponential equations, this is a skill that you will encounter later in the semester, so it's really important that you can handle problems of this type. Here, this is using the property that if the bases are exactly the same and the two things are equal, then that means these exponents must be equal to each other. So I'm going to come over here and just set up a little mini equation. If these two exponents are equal to each other, then we should be able to just solve this equation and get our answer. So if I subtract 2x from both sides, leaves me with x. If I add 1, then I'm going to get x is equal to 4. And 4 should make that a true statement. One like this, when you see one like this, we've got x's like all over the place. So it's going to be really hard to isolate the x. So on a problem like this, what we want to do is we want to take out our GCF, okay, our greatest common factor. So I've got an x squared and an x, so that means I can take one x out. And I have e to the x's for both problems, or both terms. Okay, so that means when I take out an x and an e to the x, I'm left with an x from the first term, and I'm left with a 5 for the second term. Okay, so from here, we've got 3 things multiplied together. So what we would do in a case like this, where the product of all those is equal to 0, that means one of them, at least one of them, has to be equal to 0. So I'm going to set x equal to 0. I'm going to set e to the x equal to 0. And I'm going to set x plus 5 equal to 0, because that's the 3 things that are multiplied together to give me 0. Okay. Well, this one's already solved. This one we can solve very easily. And then we come to this one. So we want to know where e to the x is equal to 0. If you look back at this graph here, this is a horizontal asymptote. So what happens is this graph actually never touches the x-axis. So there's nowhere that e to the x equals 0. So we don't get a solution from that. We only get solutions from these two. This one's very similar. We'll take out another GCF. So the GCF here would just be the e to the negative x. So that leaves me with a 3 here and a minus 4x over here. So I'll set this equal to 0, and then I'll set this one equal to 0. All right, this one, just like here, if I look back at that graph, this has another horizontal asymptote at 0, so it means that graph never touches 0. So this does not have a solution. And then if I look at this, I just need to solve that. So 3 would be equal to positive 4x, divide away the 4, and x is going to be 3 over 4. Okay, just to kind of give you a little bit of information about exponential growth and decay and population growth. A lot of times we'll work with models that look like this. Your C is going to represent your initial starting value. So even if you're talking about money and how fast interest is growing, whatever that initial value, which is called your principal when you're talking about money, is going to go here. And then T, of course, always is time. K is a constant depending on what you're talking about. So your K is called your relative growth rate. So in in a money situation, your relative growth rate is going to be your interest rate. But it could, if you're talking about growth of a virus or something, it could be the rate of growth of that virus. Okay, so this one we've got cholera is an intestinal disease. It's used by is caused by a cholera bacterium and multiplies exponentially. The number of bacteria grows continuously at a relative growth rate of 1.386. And so that gives us this equation here. And this n, anytime you see a little sub-zero, that's another way of indicating the starting value. So in this example, if there are 25 bacteria at the start, so that's our starting value, how many bacteria will be present in 0.8 hours? So really that's just plugging into this equation that they give us here. So our starting number of bacteria is 25. They've already found our K for us, so I don't have to do anything with that. And then the time is 0.8 hours. We want to see how many bacteria we have in 8/10 of an hour. So when we plug that in the calculator, that's going to give us our answer. Okay, so 75.76. So we can even approximate that to be 76 bacteria. And for the other one, we would just plug in the same thing, 25e to the 1.386 times 2.5. Okay, so approximately 800 would be the bacteria count after 2.5 hours. And this is why people get sick fast a lot of times, is because of how fast it's growing. So you have an initial starting value of 25, and in 2.5 hours, you're up to 800. Okay, so in this class, we're really interested in the business applications. So one of the business applications that we've alluded to is compound interest. So the interest is the fee that's paid to use another's money. Okay, so if you let somebody use your money, say for instance, if you let the bank use your money, then because the money you put in, say, a savings account, the bank uses it to make its loans, and so it pays you to be able to use your money for that amount of time. Granted, it doesn't pay you a lot, but it does pay you some. So interest is computed as a percentage called your interest rate. And so what we'll look at is we'll look at compounding the interest. So basically at the end of some type of payment period, the bank or whoever has to pay the interest. And then when they pay the interest to your account, then that interest can be reinvested at the same rate. And so you'll get interest on the interest that was reinvested. So you're earning interest on the interest. And then after another time period, you'll have interest on the interest on the interest. And so it just kind of snowballs from there. Your principal is your present value, and it's also that initial investment that we talked about. Whatever the starting value is, that's your P. It's invested at an annual rate of R. So whatever the rate is that the bank's paying, that would be the R. And it's compounded M times in a year. If you've ever taken pre-calculus, that particular textbook uses an N. It's kind of irrelevant whether you use M or N, but basically, however many times it's compounded in a year is what the M is going to be. So if it's compounded, for instance, quarterly would be 4, semi-annually would be 2, annually would be 1, monthly would be 12, and so forth. Even daily would be 365. Okay, so if we look at this example, suppose $10,000 is deposited into an account paying interest at a 7.5% annual rate with interest compounded monthly. How much will be in the account at the end of 20 years? So looking at this, we've got, this is our principal, or our present value. It's deposited into an account paying interest at 7.5%. So this is our R, but do keep in mind that anytime you're taking a percent and plugging it into a formula, you need to move that decimal 2 places to the left to plug that in. So 7.5% is going to be 0.075 for the R. It's compounded monthly, so that means the M is 12. How much will be in the account at the end of 20 years? So we want to know the amount that's going to be in the account at the end of 20 years. So 20 is going to be our T. Okay, so we're going to have our formula is the amount is equal to P times 1 plus R over M to the MT. Okay, so our principal was 10,000. The rate's 0.075. The M is 12. And so then that's going to be to the 12 times 20 for the time. Okay, you can type this in like just straight across, so long as you put a set of parentheses here and you put one that groups all of this together as well. Okay, so we would have gotten $44,608.14 is what the new value would be at the end of 20 years. So we started with 10,000, so we didn't make 44,000, but that's what the value of it would be after 20 years. So we had 10,000. We made $34,000 in interest, which is really good, but it was also in there for 20 years at a 7.5% rate, which is a bit higher than interest rates are currently here. Also, one thing I said about putting parentheses around this, if you have the ones that have the little boxes, the calculator, then you don't have to worry about that. But if you don't, then you definitely need to put that set of parentheses there. Okay, here's one for you to practice if you'd like to try it on your own. Okay, looking at this, you've got $5,000 is invested into an account at an annual rate of 9%. So our R would be 0.09. How much is in the account in 5 years? Round to the nearest cent. Okay, and it's compounded daily, so that means M is going to be 365. So we'll use that same formula. Okay. So we're going to have 5,000 times 1 plus 0.09 over 365. Again, put a set of parentheses there. And then we're going to have 365 times 5. Okay, so at the end of 5 years with a 9% interest compounded daily, it will have grown to being worth $7,841.13. And depends on how you round it. Okay. We can also have what's called continuous compound interest. So with continuous compound interest, we have a new formula, and that new formula actually uses that base of E that we talked about earlier today. So we have PE to the RT, and so everything is the same. You don't substitute anything in for the E, just use that key on your calculator. That's all you have to do. The P, the R, and the T all stand for what they did before, okay? And you only use this if it's compounded continuously. So continuously is your keyword there. Okay, so we've got $10,000, so that's the P, is invested at 7.5%, so 0.075, with the interest compounded continuously. So that automatically tells me that we're going to use what I call the PERT equation, P-E-R-T. So P-E raised to the RT power. And we're going to want to find out how much is in the account after 20 years, okay? So our principal then would be the 10,000 E 0.075 times 20. And the main thing is just make sure that this is grouped together. Okay, so this is the basically the same problem that we had earlier, except this one's compounded continuously, whereas the previous one was compounded monthly. Okay, so if it's compounded monthly, you end up with $44,608. But if you go to compounding it continuously, then you do earn a little bit more. So you get $44,816.89. Okay, here's one to try. Okay, so looking at this, we see it's compounded continuously. This one has a principal of 5,000. So this is the principal, the P, paying 10%. So that means R is 0.10. If we move that decimal 2 places to the left, our time is going to be 10. Okay, so we've got, this should be an A, the amount is equal to the principal times E to the RT. t. So we're going to have 5,000 e to the 0.10 times 10. We'll have $13,591.41.